extreme value theorem. So, like I mentioned on before, this is really just an existence theorem. So we're going to take a first look at it. And with any theorem, there's something that's really important here, and that's the word if. Because this tells us when this is true. Okay? So if we have f is a continuous function, which means it kind of flows, there's no holes in it, with only two variables, that's the only thing it's good for. We have a domain that is closed, so that means it's bound, closed and bounded. I think you need to have both, so that it's a closed area. You don't have some here and some there. It's just like a closed space, and the boundary is included, then this applies. So the thing is the type of problems we're going to ask you to apply the extreme value theorem on are going to fit that situation. If they didn't, we shouldn't ask you about them, right? And we're not going to do that. So, but if that happens, what it tells us that there are 2 points. There's a minimum point and a maximum point. Okay, and they call them x1 and y1, such and such. So, and not only are they maximum, there's an absolute maximum. Again, because it's bounded and because it's a closed domain, so it's not everything, we can say that there's going to be a high point and a low point. So that's what it does. It doesn't tell us how to find it. For that, we have to go back to what we've been doing. The good news is the way we do it is basically everything we've been doing up to this point. So it's actually kind of a good review over this little segment of content we've been doing. So how do we find those max and mins? Now that we know they're going to be there, we will find them as long as this is true. Well, we find the critical points. And how do we get critical points? We take partial derivatives, x, partial of x, partial of y. And we set them equal to 0. That's the first step. We get these critical points. And these are possibilities for the max and min. They might not be it, they might be it. We also locate the extremum on the boundary of the domain. So there's going to be this boundary area. So that's what's a little bit new, but not so much. I mean, we'll still be able to find. So we find points along there, and we basically do the same thing. And that's what as we work through this, I'll show you what this, I'll identify what we're doing here. So we've done this part before. We didn't do this so much, but we will. We sort of did it at the beginning, remember, where we were finding optimizations, and we got that, we graphed all these inequalities, and we looked where the lines intersected, and those points on the boundary, one of them would be the max or the min. That's the same concept we're going to do here. So we're going to look along that boundary. Okay, so we tie in what we started off the semester with, 6.1 and 6.2. We're going to bring a little bit of that into these derivatives. Okay, ready for the journey? Okay, so this, and I'll tell you now. If I didn't tell you when you went to the homework, you'd see these are the homework problems. So we got 3 homework problems. We're going to do 2 of them here in class, and they're exactly the same. So there's nothing even changed. You're going to see this exact problem. So I'm going to work it. If you want, again, the textbook has extra problems that you can work through, but there's also, I think, 3 problems in the exam review. Work those ones as well. But I figure let's just go through this. You get your homework done sooner too, and sometimes when you get all that kind of stuff, there's less stress and you're able to study a little bit more. Okay, so here's the deal. We've got a function, and remember it's f of xy, which is actually z. That's a third variable. So now they're making it obvious, but it's got 2 variables, x and y. It is a continuous function. It's a linear function. And then we've got these constraints which form a boundary, right? We've got y greater than 0, and also y less than 9 minus x squared. You remember how, an x squared is a parabola, right? And since it's negative, it's upside down. So we could graph these. I wanted to focus a little bit more on what we're doing, so I've already done that, and maybe I'll skip over that. This is what the graph looks like. Remember how we would, so this bottom line here is y equals 0, and I shaded below because remember, the region we want is above. So I'm using the technique from the book that we shade the opposite, or we shade what we don't want, so that what we do want is left. Okay, so I shaded below. I graphed the graph 9 minus x squared. That's what that parabola is. And again, we want below that, so we shaded above that, so that the little white section in there, that's our region. That's our feasible region. That's where there could be a min or a max. Okay? And we can kind of see here that now this region is bounded. Remember, we talked about that before. And it's continuous, so this little open area where there's a boundary, and it's there. Okay? So, and again, this was actually y1 equals, and then I shaded below the other one, y1 equals that, and I shaded above. So you could do that. The other two problems, you won't need to do this. They only gave us one where we had to kind of do this, but you can do it. So where do we know there's a minimum and we know there's a maximum. That's what that theorem tells us. I don't know if we know it, but they told us there was. Okay. So first thing, let's look for some critical points. So we take the derivative with partial with x and partial with y, set those equal to 0. So partial with x, we get 33x, so that's just going to give us 33, right? Partial of x. 14y, we take that derivative, it's 0. Take the derivative of 100, it's 0. Okay, so I got 33. So I set 33 equal to 0. Now how can I solve that? Okay, it doesn't give us a critical point. Well, let's see what happens with y. A couple of these, it works out that, so this kind of like, hey, these don't give us any points. Y, okay, 33x, that's a constant, so when I take its derivative, it's 0. Maybe I'll do that. When I take the derivative of 14y, since I'm taking the derivative with respect to y, that gives me plus 14. Take the derivative of 100, that's 0. So again, I get a constant. If I set a constant equal to 0, it's still not 0. There's no solution here. There is no critical points from this particular one. And it kind of makes sense, right? Because it's linear. We need an x squared to get a critical point. We need, because that's a possible max or min. So these guys give us nothing. So, but we know it exists, so where does it have to exist? On the boundary. Okay, so let's see the boundary. Well, there's a couple of points we can pick out right here. So we see these intersections, those are sort of corner points, and we can just pick those out. So this one, you might, if you think of it, 9 minus x squared, you solve that, intersecting with 0. So that's the intersections we're looking for. So you get 9 equals x squared. I added x squared to both sides. Take the square root of both sides, and you get that x is equal to plus or minus 3. Y would be equal to 0, right? Because that's where we're at. So we get the point negative 3, 0, and 3, 0. To figure out if these are minimums or maximums, what do we do with those points, those x and y's? Plug them back into the original function to get a value. Okay, we could do a second derivative test, but I don't think that's going to help us. And anyway, but we're going to have a few enough points where we just start plugging them in. So negative 3, 0. So we're going to have 33, negative 3 plus 14 times 0 plus 100. So that gives us negative 99 plus 0 plus 100. Negative 99 plus 100 gives us 1. So what I'm going to do is I'm going to come back here and not just do an ordered pair, but just do a triplet, right? So that 1 is a z value. That could be a maximum, it could be a minimum, but I've got to see what I get when I plug in 3. If I plug in 3, 33 times 3 plus 14 times 0 plus 100 squished there. So then I get 99 plus 0 plus 100. So that's going to give me 199. So that point 30199, that looks like, so far that would be a max, right? And the other one would be a min, but we're not quite done yet. We now need to, so those are corner points, but there's also ones that could occur along the boundary. Now, let me see if I remember how to do these. The boundary is here. We could put in y equals 0, but as soon as you put in y equals 0, and then you take the partial, you're just going to get, you're not, so the thing is you put in the boundary, and then you take the partials to find critical points on that boundary. Well, we're going to skip over y equals 0, because if you put that in, your partial is still just going to be 33. Okay, you don't get anything. But watch, if the other boundary, so we plugged in that boundary, that's not going to give us anything. If we plug in this boundary, so we plug in y equals 9 minus x squared. So what our function becomes is 33x plus 14, and this is where we put in the y. So this is what you're going to have to do with the other problems too. You're going to have to find those boundary ones. Actually, the other two homework problems you won't, because they're all straight lines. If you look at the examples, they all end up being, they're not equal to 0, but we'll give those a try. So we just need the corner points. 9 minus x squared plus 100. So notice I just took my function and I took y equals 9 minus x squared, because that's a boundary. And so I put that in for y. Now what I'm going to do, this is on the boundary, it's still the function, right? So I see if there's any critical points here, so I take the partial with respect to x. Actually, before I do that, let me simplify this a little bit by distributing the 14. So I get 33x plus 14 times 9 is 90, 36, 126. I better check the 126. See, I was right, but I don't trust my mental math at this point. 14x squared, that I can multiply by 1 still pretty good. And so then we can, there's 126 and 100 we could combine. So that's our function. We take partials, so the partial of x. 33 is just going to be, 33x becomes 33, right? We took its derivative. Take the derivative of negative 14x squared. 2 comes down, 2 times 14 is 28. X to the first power, right? So we took that derivative. And the derivative of 226, 0, so it's gone. This we set equal to 0. So we get 33, add 28x to both sides, and then divide both sides by 28. And we are going to get 1 point something, set 1.7 something. Keeps on going, but and I use a lot of decimals at the beginning just to make sure it all matches up. If we took the derivative with respect to y, what would happen? 33, that would be 0. 14, that would be 0. That would, we just get 0, so it's not, we do get, well, I guess that does give us an answer. The partial with respect to y, we end up with 0, which is equal to 0. But what we're going to really need to do is to figure out y. we plug back in this number to what was y? Y was here. Y was equal to 9 minus x squared. So that's, we use those two together. So we take that number and we plug that in for x here. So then we get our y answer is going to be 9 minus that thing squared. 9 minus, oops, this thing doesn't work well. I should bring my other calculator. Oh well, I'll do this part first. 1.17857 squared. Get 1.38902, and then we subtract that from 9, and we get 7.61097. Write out as many decimals as you need. As I was doing this last night, it was just I looked at the answers. They put all these decimals. I don't know why. So far we've got this point of 1.1. Let's round it. 1.18. Y is 7.61, and all we need now is to figure out what z is, and then we can compare it. I guess I should circle these two possibilities. Whatever we get, we will see either, this might be the minimum, this might be the max if it's in between there, or that might give us a max. So we plug in these values for this function here. So 33 times 1.18 plus 14 times 7.61 plus 100. I think that's going to give us a max. Just from, because I know 14 times 7 is a big number. You add 100 to it. I think it'll do it. I think it'll be more than 199. So, and then 33 times 1.8 is, yeah, 1.18. So I get 38.94. 14 times 7.61. 106.54 plus 100. Adding all that together, we get 240. 6 and 8 are 14. 15, because I got to carry the 1. 9 and 5, that would have been 14. 4 and 4 is 8. So this is our max. And why? Because the z value is the biggest of the 3 points that we found. We only found 3 possible points. 2 were on the corner, 1 was on the boundary. There was nothing interior because there was no max. There was no, all the first derivatives didn't work out. But these were the 3 points that were possibilities, and then we just look at the z values. That's the biggest one, so that's the max. This is the smallest one, so that's the min. And that's how we're going to do all of these. And we'll look at one other example that should be a little bit easier than this one. This was a more complicated one, so I said let's do this one first. It also ties back to what we did in 6.1 and 6.2 with those graphing those regions, right? So we see that. That's what we're doing. Does that work out okay? Yes, sir. It is it's somewhere in here. Yeah, with this function, but we're in 3 dimensions. This is the hard thing. I don't know really where it is. I know it's a z value, so it's up in the sky somewhere, but I have no idea what it is. I was going to try to graph it, but even that I didn't have the heart to do. I just said I'm probably not going to understand what it is, because it's this 3-dimensional shape that is bounded by, but it's not all of the 3-dimensional. It's kind of like, oh, look at this little piece of, this projection of it. And those are always difficult. How many of you have taken like an engineering drafting class. Used to be a big deal, but that was like 40 years ago. In high school, I took one. And you have to draw three-dimensional objects, but you have to draw like the front and the back. You have to do it with 3 drawings in 2 dimensions. Now they have computers that do all that, so we had to do it by hand. That sort of gets you to what we're doing, but I never really got good at it. So trying to visualize what's going on is just what we're thinking is analytically we've got these boundaries, got a function, and somehow that function is bounded by that. And so yeah, the max point is on the boundary. These are actually on boundaries too, because they're going to be these corner points, so it's still part of the boundary. But that's the places we're going to look. We're going to look in the interior, which that was when we take the first partial derivative. We're looking really, is there anything inside that would cause a max or a min in that shape? This one, there wasn't.
So if we had more inequalities, more equations like that, we would just continue to plug them in and then keep doing that to find all points.
Yes. Okay. And we're not going to get to, I'll show you the next example. The first example of is the first homework problem. The second homework problem I'm going to let you do is very similar to the next one we're going to do. And what they do is they bound it with a rectangle, which is a lot easier to take a look at. And we'll see how that goes. So we don't have to do too much of this. Yeah, if we had another one, we'd have to look there too, because that would form some other kind of boundary. So the boundary might become here, and then we might have something there. And yeah.
So can we use this extreme value method to find the critical points for like previous lessons we've done?
Sure.
As long as it's bound.
Yeah. Yeah. As long as exactly. Yeah. Okay. Makes sense. So, and again, what I'll do is for Friday's class, I'll prepare a little document with sort of the big points and maybe the formulas and stuff. A PDF. You can print that out if you want, or hold on to it, so it'll give you. We talked about this, and this, and these were the formulas, and these were the methods, kind of just bullet point type thing, little brief thing. And then I'll, over the weekend and hopefully before then, I'll start working through the review test or the review practice thing in there, so that there's a video for each of those. Those may be helpful in going back into the homework as well, but they will also get us focused on what type of questions are going to be on the test. Okay. So this one, the only other one we have to do. There's another one, and all that's different is the constraints here are different numbers. So hopefully you can see that what's happening here is these constraints are forming a boundary. X is bigger than 0 but less than 5, bigger than 0 but less than 5, so it forms this sort of a constraint. Y is bigger than 0 but less than 6, so we get this, and we can shade. It would have, if we could graph it, which we can't because we can't do vertical lines, but it would be that. So it's just this little rectangle. Okay. We'll talk a little bit about, we've already talked, if this line is 0, it's not going to be very helpful, but what we see here is definitely, we've got these 4 corner points, and then also we've got anything in that interior of that rectangle that might, from the original function, might form a maximum or a minimum. And we look up here and we get an x squared and a y squared, so there actually could be, it looks like there could be some critical points. Okay, so we're going to do this in a 3-step fashion. Oh, I forgot about one up there. First one, and this is the way the homework asks you, says list the corner points, find the critical points in the interior, and then find the critical points on the boundary. And the boundary, we're going to plug in these values here. Okay, corner points. Well, those all come from really the constraints here, right? So I can see 0, 0 is 1. And I'm going to leave room for a z. I'm going to calculate that z value, but I'm going to get all the points first. This point up here would be x is 0, y would be 6. And then there's this, well, I'll go with this one. This would be x is 5, but y is 0. y is 0. And this one up here, x is 5 and y is 6. So you see how to get the corner points. And again, you'll get an example with some different numbers. That's, you just go basically draw the little rectangle and you get those 4 points. These are on the boundary, aren't they? And I think they're the easiest ones to see. What we do is now we plug each of those points in to figure out what the z value is, and that's how we're going to tell which one is the max and which one's the min, is we just look for the biggest z value. I'll do 0, 0. I don't know if I'll do all of these. That's 0, that's 0, that's 0, that's 0, that's 0, plus 5. Okay. That's about as much as I can handle today. So you can plug in 0 and then you plug in 6 for y. We'll get those values. But I want to, that's kind of a tedious thing, but we could do that. I want to get the process flowing. So is that okay? We can leave that for a little bit later. Just plug in each of the xy's into the original function, right? And you get your value. So now we want to locate the critical points on the interior. Let's get this thing out of the way. So on the interior, what we do is we want the derivative of the partial with respect to x of the original function. Nothing else done to it. And we're going to set that equal to 0 and solve for it and go there. So the partial with respect to x, 3x squared, this 2 comes down, so we get 6x to the first power. 2xy, when we take that partial, we get minus 2y, right? Take the derivative of 4y squared. Y is a constant, so that's a 0. Negative 6x, that just gives us negative 6 times 1. 20y, that's a constant, that's a 0. 5, that's a constant, that's a 0 when we take its derivative. So this is our derivative. We okay with that? Okay, so again, we go back to stuff we were working on a little bit earlier. We set this equal to 0. And notice we've got both an x and a y. We can't solve it directly for something, but we could solve it for y, and then we could plug it into the other one, right? So I think that'll work. That's what we did last time, yeah? 6x minus 2y equals 6. So let's bring the 2y over. So I added 2y to both sides. Divide both sides by 2. I'll just do it individually like this. So then we get, this gives us y equals 3x minus 3. I might need some more room, but that's okay. I find that partial with respect to y, and that's where I might fit to use this, so I know this is one of the sort of constraint things. So when I take the derivative of y, that's 0, 3x squared is 0. This is negative 2x, right, because we took the derivative of y, which is 1. We come to plus 4y squared. The 2 comes down, we get 8, not 6, right? 4 times 2 is, shoot, I'm going to have problems with that the rest of the semester, I know. 4 times 2 is 8. 8y minus 6, x is fixed, is a constant, so that's a 0. Minus 20y, y, the derivative of y is 1, so we get a minus 20. Derivative of 5 is 0 because it's a constant, so that's what we get here. We set this equal to 0. And what we're going to do is for y, we're going to plug in 3x minus 3. And let's see what we get. We get 0. There's nothing really to distribute, so we got a negative 2x plus 3x, so that gives us an x. We get a negative 3 and a negative 20, gives us negative 23. And so x, add 23 to both sides, you get 23 equals x. Did I get that right? Oh, I forgot the 8. I have a problem with 8s, right? I'm just not liking them. I thought they're, oh, thank you. Thanks for catching it. Okay. Let's try this again. Negative 2x. 8 times 3. 24. Okay. I'm going to check with you guys first each time. 24x. 8 times 3, still 24. Minus 20. Okay. Negative 2x and plus 24x, those combine into giving us 22x. 24 and 20 are both negative, so they add together to give us 44. Oh, this is looking nice. Add 44 to both sides. Divide both sides by 22. 44 divided by 22 is 2. So we get x equals 2. We go back over here and we can figure out what y is by plugging in here. So then we get y equals 3 times 2 minus 3. That's 6 minus 3, which should be 3. Okay, so from down here, and we just got to the limit of what we have. Let me do it in blue. So we get the point 2, 3, and we didn't even get a plus or minus, did we? So because it's linear, so we got one critical point in there that could be a min or a max. Now it's obviously it'd be a local one, but we're just talking the absolute ones. So there's only going to be one absolute max and one absolute min. Guaranteed. That's all the theorem says. It doesn't say there might be some other places that are relative max or mins. We don't care about that. The theorem doesn't tell us anything about that. But there's one max, absolute max, one absolute min. So again, we would plug that in 2, 3 to the original, and we'd get a z value. And again, at the end, we're going to go back and compare all the z values. So I'm going to put a underline here. And again, this is in the homework, so I'll let you do it. Plug those values in and see. And I guess actually let me come over here. And these still need to be found. Okay, but there's one more thing we need to find. We need to locate any boundary points. So these are boundary points, but they're corner points. They were the easy ones to find. The boundary points are a little harder because we have to use these formulas. So we could use x equals 0. So this is that inequality else basically tells us on the boundary there's x equals 0 and x equals 5. Now, I believe if we put in x equals 0, right, that becomes 0, that becomes 0, this becomes 0. So when you take the partial with respect to x with x equals 0, you get 0. You get 0. Well, yeah, because all these y values are 0. So that's not going to give us a point, right? We don't get an x. Same thing happens if we use y equals 0, but then this is 0, this is 0, this is 0, and when you take the partial with respect to y, that's all going to go away. So I'm thinking those are ones we don't have to worry about, but what about x equals 5 and y equals 6? Okay, so we'll start with those. Let's see. Wait a minute, see if I put in x, so the x, but then the y partial with respect to y give us a value. Actually, let me back up. Let me what time is it? Got about 10 minutes, so let's I'll come back to this. Let me do x equals 5 first. Okay, so we're going to put point x equals 5, plug that in, and if we do that, we get our new function. This is equivalent to plugging in the y equals 9 minus x squared. but we're plugging in a constant. So we're going to get 3 times 5 squared minus 2xy plus 4y squared. Oops, not xy. Everywhere there's an x, we're going to put a 5. Minus 6 times 5. Not enough room. Minus 20y plus 5. Okay, so that's our new one. And actually, you should do this with each of these. And if you look at an example in the book, they go through something very similar to this. They'll plug them all in. I think the zeros, but I'm not quite sure yet. We'll give them a try. So then what we do is we take the partial with respect to x, right? I guess we should, let's calculate everything out first. 5 squared is 25. 25 times 3 is 75. 2 times 5 is 10. Plus 4y squared. 6 times 5 is negative 30. Minus 20y plus 5. We can bring all the constants together. 75 plus 5 is 80. Minus 30 is 50. So we get 50, negative 10y, negative 20y, there's a negative 30y, plus 4y squared. Now, will you agree with me if we take the partial with respect to x, that's all going to be 0, right? So we know partial with respect to x is 0. So let's take the partial with respect to, I guess I'll do that down here, partial with respect to y, because that won't be 0. We could set that equal to 0. That will give us a y value. And then you can see what we do. Derivative of 50 is 0, because that's a constant. Derivative of negative 30y is just going to be negative 30 times 1. Derivative of 4y squared, 2 times 4 is 8. Derivative of y squared is y to the first. Set that equal to 0. Okay, we can add 30 to both sides. Come up here. So I've got 8y equals 30. Divide both sides by 8. I'm going to get 8, or y equals 3 point something, right? Now I do get, at least when I take the derivative with respect to x, I get x equals 0. If I put in x equals 0 here, this would be actually a point on the line. And think about where we are. No, x can't be 0. We're at 5. So okay, so we put x, okay. This is how it works. We already set x. X is 5. Because I think where the boundary is. To be on the boundary, x has to be 5. So we are on that vertical line. So x equals 5. When we're on that vertical line, we find we actually get a critical point at 5, and then the y is 3.75. So we're over here. We didn't get all the way up to 6. We're maybe about at this point. The function is taking, that boundary point is taking on either a max or a min for that side. Does that make sense? Okay. Good. I'm not sure I make sense to me yet, but we still need to find, we plug in those 2 points and find its z value to see overall which one is going to give us the biggest z and which one's going to give us a small z. Okay. So these, we would do the same thing actually. We should do the same thing with y equals 6. So the point 6, plug that in. Take the derivative with respect to x. That'll probably give us something. Derivative with respect to y would just give us 0 equals 0, which is inconclusive. But we would take that x value, we've got y value 6, find its z value. Do the same thing with the zeros. They may or may not give us something usable. I think it'll be the same thing. We would put in a 0 for x. The partial with respect to x would go away, but we would have something like this, maybe the partial with respect to y, which would actually be some value. And what that's telling us is, I should do it over here, it's looking, when we're putting in y equals 0, we're looking along this boundary line. That it does the function itself. And again, remember we're in 3 dimensions, so this thing could be, you know, it's not just 2 dimensions. There could be some kind of a max or a min along that boundary. So when we put in y equals 0, we're finding that one. When we put in x equals 0, we're finding this one. This one up here is y equals 6. And this one over here was x equals 5, horizontal line. So that's, we're plugging in those 4 sides into the original function, take the partial with respect to x, partial with respect to y, see if we get a value. And I believe even with the zeros, we will get values for the opposite one. So we put 0 in for y, all that stuff goes away, but the partial for x will give us a different value. So we'll have 4 points here, so there's 5. This one we figured out. Let me erase this one and this one. And what I'll do is, for the weekend, I'll work the second one similar to this, but I'm going to do it on a Word doc so I can keep going down and I don't run out of space and it's not all over the place. So the other thing you're going to need to do here is you're going to plug in x equals 0, you're going to figure out what y is, and then you're going to be able to figure out what z is. You're going to do, figure out what x is, you're going to put in 6 for y, you're going to be able to figure out z. And then this point, you're going to put in, you're going to figure out what's x, but you're going to put in 0 for y, and you'll get 1, 2, 3, 4, 5, 6, 7, 8, 9. So there will be 9 possible max or min points. You plug them all in, get the z values, and whichever is the biggest z value is the absolute max. Whatever is the smallest, and it might be negative, whatever is the smallest z value will give you your minimum. Yes, sir.
How long the test is for the unit test on Friday? I feel like this is going to
Well,
do all the possibilities.
yeah, this might not be on the test. The test, so just because we have you do a homework problem, those are, yes, they're designed, but this probably is not a very good test question. We'll look at the review, and I think there are more compact questions. But I'll work through those too. Okay. Typically, if it's something like this would be like, okay, maybe there could be 1 or 2 like this. Again, because we only have 50 minutes because of the way the classes are set up. Again, I don't cut anyone off. Class will end. But the goal is when they design this to be taken in 50 minutes. So it can't be too much. It really can't. Yeah, I'm with you.
Please open any questions after.
There's usually I don't know for this particular class, usually they do have some multiple choice and some open answer. Oh, yeah. And once I do find out, I'll let y'all know. Okay. That's why there's only 3 homework problems. I got you started.
Yeah.
Take it from there. Thank you.